In this video, we're going to talk about correlation. This is the relationship between two different variables, the independent variable and the dependent variable. So let's first discuss the differences between the two variables. The independent variable can be controlled or manipulated. This is the one in which the experimenter wants to make the adjustments to see what is happening. So you can change different items that you're talking about. So this is the independent variable. The dependent variable cannot be controlled. Then, because we're talking about correlation, we're talking about two variables in which we're going to graph on the same axes. And so the independent variable is designated by the x. So it is your x variable. And the dependent variable is your y variable. Now sometimes these are used by different names. So the independent variable is also known as the explanatory variable, meaning it can explain the differences a little bit. And the dependent variable is your response variable. Let me adjust this just a little bit. Erase this and try to rewrite that. So let me grab that back, and so your dependent variable is known as your response variable. It is the one that responds in a relationship due to the independent variable. Now then, the determination of x and y variables is not always clear-cut. Sometimes it's an arbitrary decision. And so, depending upon the experiment and upon the research, some researchers may use one item as an independent variable, while another researcher may use that same variable as the dependent variable. And so it's not always going to be the same for every single research value. When we are graphing these, we are going to put them on what is considered a scatter plot. And so let me draw a couple of scatter plots to kind of illustrate what's happening. A scatter plot is where we just have, here is our y-axis, and here is our x-axis. And then a scatter plot is, because we're looking at dependent and independent variables, they are like points on the graph. And so we're just going to place those points wherever they would occur. So this could be a generic scatter plot. Now each scatter plot is going to be a little bit different, and the scatter plot can help us determine whether there's a relationship between the two variables or not. So let's look at a couple of those. And the first one I'm going to draw, here's our y-axis and our x-axis. And I'm going to put on here some points that would be along our scatter plot. Okay, so looking at this, notice that they're fairly close together, and they're what we consider in a positive linear area. For a scatter plot, we do not connect the dots. We just literally put the dots on the graph and leave them. And so this right here is positive Because what happens is as the independent variable, the x-axis, so this is our independent variable, whereas remember our y-axis is our dependent variable. And so as the independent variable increases, our dependent variable also increases. And this is what we call a positive linear relationship. Because if you notice, we can almost draw a line, and it's got a little bit of a positive slope in there. And we'll talk later about how to actually get this line, and that line is not very good. Later on, where we do put these in there, we'll draw them a little bit better. But we'll talk about how to get this, and remember that slope is how quickly we go up and we rise and we run. Let's look at another way that this could look. And that would be if I had this. This is my x. This is my y. Still the dependent variable goes along the y. The independent variable goes along the x. And this time the dots are going to be looking like this. Okay? And so what's happening is as the independent variable is increasing, the dependent variable is decreasing. And so this is what we call a negative linear relationship. Because we could almost draw this line down through here, and it would have a negative slope. Let's look at two more types that look like this. Here's my x and my y coordinates. And then wherever I put them on the graph, if I put my points on a graph, notice this one is not very linear. It has, you can see a very distinct little curve there. And so this one is actually what we would consider a non-linear relationship. There is some type of relationship there because you can see that as they are put on there, you can see a shape of some sort, but it's not a straight line or anything because as it comes up, then it goes back down, and so it's going to be a non-linear relationship. Another type that we have, here's the x, here's the y, is if I do points that kind of are all over the place, okay? Notice there's no real shape to this. I can't draw really a straight line through them either direction. There's not a type of curve or anything. And so this one is literally no relationship. I like to call it the buckshot method because it just scatters everywhere. And so these are the four different types of graphs or different relationships that we really try to look for. Is there some type of positive linear, or is it a negative linear? Is it some type of non-linear, like this one? Or is it going to be no relationship at all? So let's look at an example of this. So for example, we're going to talk about deaths from lightning. And we're going to use the numbers of this in several of our examples throughout this video. But deaths from lightning. And what happens is one of the national organizations keeps track of not only the deaths from lightning each year, but also the circumstances under which those deaths occur. And so they're going to look, they gave us the values for death under a tree and other types of deaths. So we have this table that we're going to have. So people died under a tree from lightning. And then there were other types of deaths from lightning. And remember that these are all from lightning, okay? And so our table, in one year, there were 8 deaths under a tree, and there were 21 other deaths. Another year, there were 5 deaths under a tree, and 29 other deaths. Then 13 and 34, 6 and 36, 11 and 40, 9 and 37, 6 and 26. So I have my x variables and my y variables, and think of this like we are plotting points. This is your x value, this is your y value. And remember, plotting points on a graph, you do x comma y. Okay? So I'm going to come here and try to draw a little bit better my graph. And so this would be my y-axis, this would be my x-axis. And so this down here is deaths under a tree. And over here we have other types of death. Okay? And so notice that under a tree we range anywhere from 5 up to 13. So I'm going to come down here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Hopefully sometimes we can have those evenly spaced. Now then the other types of death, notice that we range from 21 up through 40. So I'm going to have to make my lines a little bit different. Okay, these should be counting by twos. So 2, 4, 6, 8, here's 10, 12, 13, 14, 15, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 is at the very top. Okay? And then we're going to plot our points. So our first point is at 8, 21. So I'm going to come over to 8. So 2, 3, 4, 5, 6, 7, 8. And then I'm going to go up to about where 21 is. This would be much easier on graph paper. Then 5 and 29. And so I'm going to come up to about right here. 13 and 34. It's going to be about there. 6 and 36. Be about right there. 11. And 40, so oops, don't want that. Let's erase that back. I don't want a line on there. So 11 and about 49 and 37. It's going to be a little bit up from those. And then 6 and 26 would be about right here. So I have all 7 of my points plotted. Now I'll be honest with you, I'm not seeing much of a pattern. Now it could be because my scale is a little bit off. Like I said, it's better if we draw it using a graph paper and everything, but I'm not seeing much of a pattern. We can draw our graphs and everything, and we can look at them, but that doesn't exactly tell us how strong a relationship is or anything. What we need to determine that is the correlation coefficient. What we call the correlation coefficient. This is used to determine the strength of the relationship. Correlation coefficients, there's dependent upon whether you're talking about the population or the sample. So population correlation coefficient, and a sample, which normally whenever it's just a sample, we just call it the linear coefficient, correlation coefficient. A little bit of differences between these two. Now obviously this is from the population, this is going to be from a sample. So I'll go ahead and put from a sample. And this other one is from the population. The population, remember when we're talking about population, we usually use Greek letters. And the Greek letter for this one is what we call rho. It looks like a P, but it's the Greek letter rho. Then for sample, we use the letter R. For both of these, we talk mostly about the linear correlation coefficient, the one from the sample, because very rarely do we have the population. So we usually talk about this one, because what we're going to do is we're going to end up using the R to predict about the population. Remember, we make those inferences and we predict about the population. And so a couple of things is that R must be between -1 and a +1. It can be negative because remember we're talking about a negative correlation or a positive correlation, but it has to be between -1 and +1. The closer to a 1 it is, the stronger the relationship. R is also sensitive to the outliers. We've discussed outliers before and how to calculate those. The correlation coefficient is extremely sensitive to those because you have one outlier and it's going to pull that number way off, okay? And so when we're looking at the scale between a -1 and a +1 for our correlation coefficient, with 0 being in the middle, if we have a -1, that means that there is a strong negative linear relationship. So the closer to a negative one it is, the stronger negative relationship it is. For the same thing happens on the positive one side. It is a strong positive linear relationship. And remember, it's linear because we're looking for that straight line. Okay? The closer to 0 it is, the closer to it having no linear relationship. And it doesn't matter if it is positive or negative. The closer to 0 it is, the further away from having a linear relationship it will be. Our problem comes in when we want to find the R. How do we calculate this R value? So we have one of those nice little formulas. And I say little as I draw a big fraction bar. It is n times the sum of x times y minus the sum of your x's times the sum of your y's divided by, and we have the square root of n times the sum of x values squared minus the sum of the x's and that value squared times n times the sum of the y values squared minus the sum of the y's and that value squared. Now I realize that this looks like an awful formula and everything else. I'm going to show you how you can put it into a table to help you solve it out. And then I'm also going to show you a shortcut or shorthand way of looking at this formula based on the columns that you put into the table. One thing, we always want to round our R to 3 decimal places. So we always round our final answer to 3 decimal places. If you're rounding in intermediately and it's not your final answer, always take it out about 2 places more than what you want your final answer to be. So in this case, you would take all your numbers out to about 5 decimal places. Okay? So what we're going to do is we're going to make a table, and it's going to have 5 columns. And I'm going to call them column A, column B, column C, column D, and column E. Column A is going to be your x values. Just literally write down what your x values are. Column B is going to be your y value. So in here, we should have the first row for x and y being the point that we would put on a graph, our x value and our y value. And we do that all the way down. Column C is going to be x times y. So we're going to take our x value and multiply it by our y value to get column C. Column D is going to be the x values squared. And column E is going to be the y values squared. And we want to find the sum of each of these columns. So whenever you get done, you should have a sum in each of these columns. Those sums are what we're going to put into the formula. The n value, n is equal to the number of rows. How many x's did you have? how many y's did you have, and you should have the exact same number. So when we look at the formula again, remember I had it up here, and it looks kind of crazy, but n is going to stay in, so I haven't changed that. Then the sum of x times y. Well, x times y is in column C. So we're going to say n times column C minus the sum of your x's times the sum of your y's. Well, that's columns A and B. So minus column A times column B. And remember, whenever I put these in here, I'm talking about the sum of these values. Okay? And then I have the square root of n times the sum of your x squareds. So that's this column. So that's going to be column D minus the sum of x's squared. So that's going to be column A squared. We're going to multiply that by n times the sum of your y squareds. So that's column E minus the sum of your y's, which is column B, squared. So if you do this table out, these column totals is what you're going to be putting into the formula. The n, again, is the number of rows. How many different types of points did you have, basically? Okay, so let's do an example. And the example that we're going to do is continuing to work with the deaths from lightning. So we're going to continue with the deaths from lightning. And so we had under a tree, and we had other types. Whoops. Need to correct that there. So we had other types. Okay, and so I had 8 with 21, 5 with 29, 13 with 34, 6 with 36, 11 with 40, 9 with 37, 6 with 26. And we want to make those 5 different columns. So I'm going to have column A, which is going to be our x value. Then I'm going to have column B, which is our y. Column C, which is x times y. Column D, which is x squared. And column E, which is y squared. So my x's are 8, 5. I'm going to need to move these closer to fit them into my screen. So let me erase those a little bit and start again. So let's go with 8, 5, 13, 6, 11, 9, and 6. Then we had 21, 29, 34, 36, 40, 37, and 26. Then in column C, what I'm going to do is I'm going to take 8 times 21 and get 168. Then I'm going to take 5 times 29 and I'll get 145. Then I'll take 13 times 34 and I'll get 442. I'll take 6 times 36, which is 216. I'll take 11 times 40, which is 440. I'll take 9 times 37 and get 333. And then I'll take 6 times 26, and get 156. So that has given me my columns A, B, and C. And eventually I'm going to add them all up. Okay. Column D is x squared. So I'm going to take 8 times 8, which is going to give me 64. I'll take 5 times 5, which is 25. 13 times 13 is 169. 6 times 6 is 36. 11 times 11 is 121. 9 times 9 is 81. And 6 times 6 is 36. Then my last column, which is the y squareds column. That means I'm going to take 21 times 21, and I'll get 441. 29 times 29 is 841. 34 times 34 is 1156. 36 times 36 is 1296. 40 times 40 is 1600. 37 times 37 is 1369. And 26 times 26 is 676. So I now have each of my columns filled out. The next step to do is to sum these up. So I want to get the sum of each column. So I'm going to add all of these up. So I'm going to take 8 plus 5 plus 13 plus 6 plus 11 plus 9 plus 6, and I'm going to get 58. And I'm going to do the same thing, 21 plus 29 plus 34 plus 36 plus 40 plus 37 plus 26, and I'll get 223. In column C, I should get 1,900. In column D, I should get 532. Please stop the video at any time and check my numbers, and to make sure that you can get these same numbers. And if you're having trouble, call or email me, okay? Column E should be 7,379. So I have the sum of each of my columns. The only other thing that I'm going to need is my n. Remember, the n is the number of rows. I've got 1, 2, 3, 4, 5, 6, 7 rows. So that is what my n is 7. Now then, I can put this into the formula. R is equal to n, which is 7, times the sum of x times y, which is column C, 1,900, minus the sum of your x's, which is column A, which is 58, times the sum of the y's, which is column B, 223, divided by the square root of n, which is 7, times the sum of your x values squared, which is column D, so that's 532, minus the sum of your x's, 58, and that value squared, times your n, which is 7, times the sum of the the y values squared, which is column E, which is 7,379, minus the sum of the y's, which is 223, and that value squared. So I now have my formula filled in. Now it's time to calculate it. And I would go through there and do it a little bit at a time to make sure that you get it correct. I would do the multiplication, each multiplication first, and then each subtraction. Okay? So 7 times 1,900 is going to be 13,300. 58 times 223 is going to be 12,934. 7 times 532 is going to be 3,724. 58 squared, which means 58 times 58, is 3,364. 7 times 7,379 is 51,653 minus 223 squared, which is 223 times 223. That is 49,729. Okay. Then let's do all the each individual subtraction. So 13,300 minus 12,934 is going to give me 336. 3,724 minus 3,364 is going to give me 360. And then 51,653 minus 49,729 is going to give me 1,924. So I still need to do the multiplication on the denominator. So that's going to be 336 divided by the square root. 360 times 1,924 is going to give me 692,640. Then I'm going to take the square root of that 692,000, and that is going to give me 832 and 96. Because remember, I want to round this to 3 decimal places, so I want to keep at least 2 extra decimal places in the meantime. Okay, do this division, and I want to check and make sure that I did do the division correctly. So 336 divided by the 832. So that should give me, where I rounded off, 0.04. This is my correlation coefficient. So it's not real close to 1, but it's not very close to 0. It is positive, and so there is a moderately positive linear relationship in this case. And so you're going to do this calculation anytime you want that correlation coefficient. The reason why we do correlation coefficients is so that we can use hypothesis testing for these. In the hypothesis testing, we're going to use table F, which is your t-value table, and in this case, for the hypothesis testing, so we're again looking at hypothesis testing. We're not going to be using the z-score like we have in previous ones, or the t-value or anything. For correlation coefficient, we want to look at our null hypothesis. It's going to be rho, and usually we're just seeing if there's a difference, if there's significance. So we're going to use equal to and not equal to. The equal to portion says that there is no correlation between the population, between the variables in the population. The alternative hypothesis is going to say that there is significant correlation. So this one, there is significant correlation between the two variables based on and this is in the population based on the sample that we have. The test statistic that we are going to use is T is equal to R times the square root of n minus 2 divided by 1 minus R squared. And so you're going to do the R squared and then take 1 minus that. Remember, with T values, we have to look at degrees of freedom. And since we have two variables, our degrees of freedom for this case is n minus 2 because we're looking at two separate variables. And we have to make sure that we know that because it does change the way that we look up our values in the T table, which is table F. Okay? So let's continue with the death from lightning as our example and see if that correlation coefficient 0.04 that we had found, see if there is any significance to that. So we're talking about deaths from lightning still. We had already found that R was 0.404 and we want to use alpha, this case 0.05, and we want to test the significance. Of the correlation coefficient. Okay. And so if we're just wanting to test the significance, if there is any significance or anything, we're going to use that our H naught rho is equal to 0 and H1 rho is not equal to 0. Now recall back from our chart that we had, our n was 7. So that means that the degrees of freedom that we're going to use is n minus 2, which is going to be 5. And this is important because remember, when we look up those critical values for our distribution, because remember we're going to draw the normal distribution. This is a two-tailed test since it says not equal to. And so I'm going to put on here and shade my tails. But I need to look up what that T value is. And that T value is based on the degrees of freedom of 5 and our alpha as being 0.05. So go to table F. So this is table F that we're looking at. Go down the degrees of freedom to 5 and then across to where it says two-tailed is 0.05. When you do, you should find the number 2.571. And we're going to use a positive value and a negative value for our critical regions. Okay? because we want both sides of this. Our next step is to do our test statistic. And that is going to be t is equal to r square root of n minus 2 divided by 1 minus r squared. Our r is 0.404 times the square root. Our n was 7 minus 2, and that's going to be 1 minus 0.404 squared. Okay, so I'm going to work this out a little bit. That's going to be 5 divided by a 0.836784, and then I get a 0.404 times the square root of, I'm taking 5 and dividing it by 0.083784, and I get 5.97526. Take the square root of that, and I get 2.4444. Multiply those, and I want 3 decimal places, so that's going to be 0.988. And the reason I want 3 decimal places is because our t values are also 3 decimal places. So my 0.988, when I put it on my chart, 0.988, is here in the middle. It is in the not shaded region. Since it is in the not shaded region, remember that means that we do not reject the null hypothesis. And that signifies that there is not a significant linear relationship. So there is not enough evidence to say that a significant linear relationship exists. And usually I would say between the number of lightning deaths occurring under a tree and the number of lightning deaths occurring in other locations, but making sure that we say that there is a significance or there is not a linear, significant linear relationship, that is the most important part. Okay? So you're going to really need to practice the tables, and those tables are going to come in handy when we begin discussing regression. So please pay attention to them. And if you have questions, please let me know, and I'll be glad to answer.